Hello class again and welcome to this particular video, and in here we're going to continue from where we stopped involving kinematics. And take note that in our kinematics video we're able to talk about the two types of quantities involving motion. One type of quantity involves scalar quantity while the other is considering the opposite, which is a vector quantity. Take note that the scalar quantity is having only the magnitude that is expressed in its description, but doesn't account for the direction. However, on the other side of the aisle, which involves a vector quantity, they not only describe the magnitude, but also describes the direction. And we looked at various examples of these here involving scalar quantity. We talked about, in this case, distance. And take note that the distance in this case is expressed as the letter D. And take note that this is measured in meters, but doesn't explain further in terms of the direction. However, on the other side, vector example involves the use of a position description, and the position, which is expressed as D with the vector arrow sign on top of it, is connected really well to another specific vector quantity, which is called displacement. And displacement tells you the specific change in position of an object. And when this object is in motion, we not only express the displacement as our change in our position vector, but also you can determine the change in the total position of our object. So, what are these two particular symbols and what do they imply? To figure out this one right here, what we need to do is take note of the change in our specific position to be the position final minus the position initial. So where the specific position of the object is at the beginning versus the other at the end, that gives us our specific change in the position, which is the displacement. However, on the other side, when we have more than one movement or positions of vector associated with our object, in this case here, we are expressing our change in our total displacement to be expressed as the change in one particular position of an object plus another position of that same object. And so these two changes could be more depending on how many vector arrows you have in this particular case right here. So please take note of all this in terms of the association between the position and the displacement that is accounted for in this particular case. Now, take note here that in this case here, in terms of the position, and indeed the displacement, our unit is not only expressed as that of meters, but also it tells you the direction or position where the particle or object is located at. So in here, this is based on our specific coordinate system that tells us our north, east, south, and west positions. So depending on which cycle of our particular arrow is positioned, that tells us the location precisely of that particular object. So take note that there's one more variable we need to introduce in terms of quantity, which is now involving time. And we need time in this particular case right here because the time interval now brings us to where we are going to be focusing on, which means when an object starts at a particular position, it has a specific time, and when it moves and stops at another point or position, that is recorded as another time. So the time interval that we are going to be focusing on is not only going to be associated with our scalar quantity in terms of distance, but also our vector quantity, which is expressed as the change in the position of that particular object. And so what we see is that when our time which is in this case going to be expressed as a denominator in this particular connection with the scalar quantity, and we have our distance, which is expressed as the numerator in this particular relationship. This gives us a new scalar quantity which is called the average speed. And the average speed, take note, is symbolized as this particular V with a subscript that is AV, and this, take note, is considered to be a scalar quantity. And this is not only symbolized as V with subscript AV, but also these can be determined by the connection between the distance, which is measured in meters, and that of our time. And so therefore, to determine the average speed, what we need to do is to find our change in our distance divided by our change in our time. And so therefore, we are able to get our unit of our average speed to be, in this case, meter per second. And so this can show you many things. If I want to determine the time from our average speed, all I need to do is do the following. All I need to do is, for our change in time, which is our time interval, we divide our change in distance by our average speed. While on the other side here, to go from our average speed to a distance, we need to be able to multiply our average speed by our change in time, which is the time interval. So please keep this relationship in mind, and while we're done with that, we are going to associate our time interval now with the vector component. And so the vector component comes in various forms, and these forms here shows a couple of things to keep in mind. One is that we need to associate our position vector with that of our time. And where on one side here, this position vector is going to be shown to be linked or recorded in the vertical axis region, which is of course measured in meters with our specific direction or position of our specific object, but also our particular time is going to be recorded on the horizontal axis, which is on the x-axis, and this is recorded in seconds. And so what we have when we associate our time interval with our position vector is the production of our specific recorded result, which is called a position time graph. And so what our position time graph does is that, one, it describes the motion of an object based on the vector quantity relationship. And so therefore, what we have as our measurement is that on the y-axis, we have our position, and our position is going to be recorded, take note, in meters, and our specific direction that it is located at. And take note that the symbol for our position is recorded as D with the arrow at the top, and this is going to be plotted against the horizontal, which is our time interval, which is recorded in seconds, and it is expressed as T. So since we have these, take note that our graphs comes in various ways, but overall we need to be able to determine, take note, the slope of this particular straight line. Now we're going to focus on a straight line. In this case, the straight line is a positive slope in this part here, and to determine this particular relationship, all we need to do is to find our relationship between our y change, which in this case here is measured as our position final, and this is measured as the position initial, and on the other side here we're going to be measuring our time, which is in this case our final time, and our time initial. And take note here that the space between the time final and the time initial is a measured as t final minus t initial, and on the other side here, dealing with our specific position change, what we need to do is you do the position final minus the position initial. And so this comes into play when we are trying to figure out the slope of this particular line. And so therefore, the slope of this particular line is expressed as the measure of the steepness. How steep is our specific line? And now this slope is rightly connected, always connected to a particular variable, which is not only expressed as m, but also in terms of the position time graph, it is expressed as our average velocity. And so therefore, our average velocity is equal to rise divided by our run, where our rise is expressed as our specific variable operation here, and our specific run is expressed as this particular variable expression over here. Take note that this is rise, not run. So therefore, our rise over run is equal to, take note of our final position minus our initial position, all divided by our final time minus our initial time. And so therefore, we are able to re-express our final position minus our initial position in terms of what we have over here, which is expressed as our displacement, which is a change in our position. And so therefore, this is equal to our change in our position divided by our change in time. And this is how you're able to determine the average velocity of our specific object, and how this is truly different from the average speed, because the average speed just takes into account the total distance. However, the average velocity takes into account the total displacement or the change in our position. So therefore, this is not only expressed as this, but also can be expressed as the final minus the initial, or divided by t final minus t initial, or you can express these as a total displacement change divided by our specific time. And so therefore, we are able to explore average velocities through the slope of our position time graph. There are various forms of our position time graphs that we're going to talk about on our future videos. We're going to look at straight lines that shows uniform velocity, where we have our position with respect to time. And on the other side here, we're going to have another case scenario where we don't have uniform velocity, when we are analyzing our position with respect to our time, and where this one here just tells us zero acceleration, this one over here gives us accelerating object. So thanks for following me through this long video. I hope you're able to understand this connection between average velocity as a vector with that of the position and the time graphs, and this in comparison to the scalar quantity, which is related to the average speed when we are connecting our distance with the same time interval. All the same, see you on the next one. All the same, stay smart as always and believe in yourselves.